I will introduce our latest word-to-speech translation. I'm the presenter Rong from the machine translation team at ByteDance AI Lab. Speech-to-text translation is to read the audio signals of speech in one language and translate to the text in another language. There are wide applications of speech translation tasks. For example, when we watch the foreign videos, when we travel abroad, or in the global conferences, we all need speech translation systems to help us to understand the content. Traditionally, the Cascaded model is pretty popular. That is, to first go through an automatic speech recognition model to get the transcription, and then go through a machine translation model to get the final result. However, there are two main challenges. First, it is computationally inefficient. Second, it is likely to encounter the error propagation issues. When we get errors in the transcript from the ASR system, the wrong recognition result will bring wrong translation. So, to better fix these two problems, the end-to-end model is now becoming a new trend in the research area, like an encoder-decoder model, a single model to produce text translation from speech. Classic models like LSTM and speech transformer. It is often claimed that the end-to-end model is simple to deploy, and we are also expecting to relieve the error propagation problem that often occurs in the cascaded system. However, training a single end-to-end model is not easy. There are problems like lack of large-scale annotated datasets, modality disparity between speech and text, and for product serving, you must consider the latency feature. Among these problems, data scarcity is the most frequently mentioned. As we all know, there are a huge amount of parallel byte text, like in English to German WMT dataset, there are more than 40 million pairs of sentences, and this brings good translation performances. However, the largest English to German speech translation dataset only has a few 100,000 of sentences for training. And for other languages like English to Japanese, the scale is even smaller. With such small dataset, we cannot guarantee an end-to-end speech translation model to have a good performance, for we are very likely to encounter the overfitting problem. So, how to solve the data scarcity problem? In this work, we give two straightforward solutions. In brief, the first is to fully utilize the existing speech transcript translation triple data. The second is to introduce the large-scale machine translation text data to help the training in the speech-to-text model. In detail, motivation 1, that is to fully utilize the ST triple data, we find that for each parallel supervision, we can decompose them into three subtasks, ST, ASR, and MT. This makes a multitask learning framework. For the second motivation, we try to introduce larger scale MT data and well-trained MT model to improve the ST performance. So here comes our framework, Cross-speech text network, also known as XSTNet. The model can accept either audio input or text input with a classic transformer module shared for both modalities. To the green part of the model, it is a transformer model, and intuitively, we can add more external MT data to train the shared transformer encoder and decoder. Move to the part that is specially designed for the audio input. We use self-supervised pre-trained wave-to-vector-2 model and two convolution layers as the acoustic encoder. Since we mentioned that we adopt a multitask framework, we use different language indicators to distinguish MT, ASR, and ST tasks. This strategy is also commonly used in the multilingual translation. Also, I would like to show how to add special token audio to the speech. We just simply concatenate the lookup embedding of special token audio to the beginning of the compressed representation of the audio input from the acoustic encoder. We also designed the progressive multitask training strategy. It has two stages. We first pre-train the transformer module using large-scale external MT datasets like WMT datasets. Then in the second stage, we adopt the multitask fine-tuning. We merge both in-domain and external datasets. All the data, including external MT dataset, speech translation supervision, speech transcription supervision, transcription translation supervision. And we call the process as progressive since we highly recommend you to continue training the external MT data in the second stage. And later, in the experiment part, we will show that the training strategy works pretty well and the little differences in the training trick will make large impact on the final performance. To test the speech translation performance, we do experiment on master C datasets, and we find that XSTNet works pretty well, and the base version is trained only using master C dataset itself and applying the multitask learning framework, and achieves the SOTA in the restricted setup. And the expanded version goes even better by utilizing external MT data and progressive multitask training tricks. Comparing to the baseline models, there are more than 3 points of growth in terms of the BLEU score. We also find that end-to-end XSTNet expand model is better than the cascaded model. And for a fair comparison, we implement a strong cascaded model with a strong ASR model and MT model trained from large-scale datasets. And we surprisingly find that the MT performance can be even improved by 1.5 BLEU by adopting a multitask framework. We attribute this part of the gain from the audio information. Also, the word error rate is decreased, and these findings verify the robustness of the multitask strategy. And previously, in the method part, we emphasized the progressive multitask training strategy, and here we do ablation study on English to German, French, and Russian to empirically show that small training tricks make large impact on ST performance. First, we find that multitask fine-tuning is much better than fine-tuning only on speech translation ST supervision. This is pretty different from what we find in other NLP tasks. And we will get an average of 2.1 BLEU increase if we apply multitask fine-tuning, and we claim that this is due to the small scale of the dataset, and the multitask training makes the model less likely to overfit the training set. Second, MT per-training in the first stage is necessary, even if these data are also trained in the second fine-tuning stage. This makes a 1.2 BLEU improvement, and we also find that the more extra MT data, the better performance in the speech translation task. Third, do not stop training the data in the previous MT per-train stage. Continue using the extra WMT data, and you will get 0.3 BLEU improvement on average. And finally, I would like to show some cases to compare the end-to-end model with the cascaded system, and in what cases our model is better than the traditional cascaded model. The demo is from TED Talk. Listen.
You can go on the website, download all the design files, make them yourself.
And we find that the ASR model recognizes all the design files as other design files. This brings long translation of the cascaded system, while the end-to-end XSTNet gives the correct translation. This is the second case.
Lights, sounds, solar panels, motors, everything should be accessible.
In this case, the transcription generated from ASR model is correct. However, since we do not know the right punctuation, and finally, the Cascaded system gives a ridiculous translation while our model is correct. And finally, the key takeaways of our work is that we designed cross-speech text network XSTNet, a multitask training model that can accept bimodal input and extra empty data. It is extremely concise, no need to do knowledge distillation, no fancy losses, but has excellent performance. And second, we claim that the training process really matters. Like in this work, we propose the progressive multitask training tricks, and we find that to train an end-to-end speech translation model, MT per training is necessary. Also, optimizing the multitask losses is much better due to the small scale of data. And last but not least, continue using the external MT data, and that is to train your model progressively. Thanks for your listening. Here are some useful links, and we've open sourced all the codes and models, and we will keep updating some interesting demos and the TensorFlow serving at the product page. And finally, I would like to do some advertisement for other related works like Neural ST code base, where my code is built based on it. It is pretty easy to use, and you are also welcome to try our translation product, translate.volcanoengine.cm. That is all for my presenting. Thank you.